Bismillah ar-Rahman ar-Rahim. We have two n-dimensional complex valued random vectors x and y. They are circularly symmetric Gaussian. The mean of each is the O0 vector. The covariance matrix of each is identity of size n by n. The two vectors are independent of each other. We are interested in the probability density function of rho. Rho is the square of the magnitude of the inner product of vectors x and y divided by the product of the L2 norm of each. We can rewrite rho as 1 over the L2 norm squared of vector y times the magnitude squared of x over the L2 norm of x, Hermitian, times y. Let's focus first on this inner product. Given random vector x, this is an affine transformation of Gaussian random vector y. Given x, this inner product is Gaussian. To characterize the Gaussian PDF, we need the mean and the variance, the conditional expectation of x Hermitian y over the L2 norm of x, given x is x Hermitian over the L2 norm of x times the expectation of y given x. Y is independent of x. The mean of y is the O0 vector. Thus, the conditional expectation is equal to 0. If we want to compute the variance, we multiply this quantity by its complex conjugate, which is its Hermitian. When we compute the conditional expectation given x, we get 1 over the L2 norm squared of vector x, x Hermitian. Then we have the expected value of y Hermitian given x. That's identity of size n by n. Then we have x. X Hermitian x is the L2 norm squared of vector x. So this ratio is equal to 1. The conditional variance is 1. Nothing here depends on any element of x. So the unconditional distribution of this inner product is Cn01. The magnitude squared is distributed as 1/2 a chi-squared random variable with 2 degrees of freedom. This is an exponential with a mean of 1. The ratio rho is this exponential random variable divided by the L2 norm squared of vector y. Given matrix P, vector y can be written as Py plus identity of size n by n minus P times y. We choose matrix P here to be an orthogonal projection matrix. Specifically, we choose matrix P to be the orthogonal projector onto vector x. P can be written as 1 over x Hermitian x times the outer product of vector x with itself. If we have two vectors alpha and beta, and we are interested in the L2 norm squared of alpha plus beta, we get the L2 norm squared of alpha plus the L2 norm squared of beta. We also have alpha Hermitian beta plus beta Hermitian alpha. So when we compute the L2 norm squared of vector y, we get the L2 norm squared of Py plus the L2 norm squared of identity minus P all times y. We then have the cross terms, so we get P Hermitian, identity minus P. P is an orthogonal projection matrix, so it is Hermitian. P Hermitian is equal to P. It is idempotent, so P squared is equal to P. P Hermitian times identity minus P is equal to P minus P, which is the O0 matrix of size n by n. The cross terms here are equal to 0. The L2 norm squared of a vector is the Hermitian of the vector times the vector itself. But P is an orthogonal projector. B Hermitian is P, and P squared is P. So this quadratic form is y Hermitian Py. If P is an orthogonal projector, identity minus P is an orthogonal projector. In our case, identity minus P will be the orthogonal projection matrix onto the subspace that is orthogonal to vector x. This L2 norm squared is the quadratic form y Hermitian, identity of size n by n minus P times y. If we do eigencomposition to this orthogonal projection matrix, we get Q, the unitary matrix of eigenvectors, lambda, the diagonal matrix of eigenvalues. For a projection matrix, these are 1s and 0s. The number of unity eigenvalues is the rank of P. In our problem, P has a rank of 1. The eigendecomposition is Q lambda, then the inverse of Q, which is Q Hermitian, as Q is a unitary matrix. Then we have Y. This quadratic form can be written as Y Hermitian, Q tilde Hermitian Y. The columns of Q tilde are the eigenvectors of P corresponding to the unity eigenvalues. The L2 norm squared of vector Y can be written as the L2 norm squared of vector Q tilde Hermitian Y plus the L2 norm squared of the vector identity minus P times Y. If Z is a circularly symmetric Gaussian vector, its mean is the O0 vector in m-dimensional space. Its covariance is identity of size m by m. If omega of size m by m is an orthogonal projector with rank k, then the PDF of Z Hermitian omega z is that of 1/2 times a chi-squared random variable with 2k degrees of freedom. This is true if omega is deterministic or if it is a random matrix with random variables that are independent of the components of vector z. If we go back to our problem, matrix P is an orthogonal projector with a rank of 1. Identity minus P is an orthogonal projector with the rank of n minus 1. These two orthogonal projection matrices depend on x, but x is independent of y. This quadratic form has a PDF that is 1/2 times a chi-squared random variable with 2 degrees of freedom. The PDF of this quadratic form is the PDF of 1/2 a chi-squared random variable with 2 times n minus 1 degrees of freedom. We need now to investigate the dependence or independence of these two quadratic forms. Given random vector x, these two vectors are Gaussian because they are affine transformations of Gaussian random vector y. They are both 0 mean. What about their cross covariance? The expectation of Q tilde Hermitian y times y Hermitian times identity minus P, given x, is Q tilde Hermitian, the conditional covariance matrix of vector y given x. Y is independent of x, and its covariance matrix is identity of size n by n. Then we have identity minus p. This is equal to Q tilde Hermitian Q tilde Hermitian times identity minus p. In the general case, this is the identity matrix because the columns of Q tilde, which is taken from Q, are orthonormal. In our case here, this is just the scalar 1 because Q tilde is a column vector with unity L to norm. Q tilde Q Hermitian is orthogonal matrix P itself. So this is equal to Q tilde Hermitian P times identity minus P. This is the all-zero matrix as we get P minus P squared, and P is idempotent. So P squared is equal to P, and their difference is the all-zero matrix of size n by n. Given x, Q tilde Hermitian y, and identity minus P times y are jointly Gaussian random vectors. Given random vector x, they are uncorrelated. Because they are jointly Gaussian, then they are independent given x. If we stack Q tilde Hermitian y on top of identity minus Py, this is equal to Q tilde Hermitian, then identity minus P. This n plus 1 by n matrix is multiplied by vector y. The random variables in vector y are independent and identically distributed Gaussian. So the components of vector y are jointly Gaussian. Y is a Gaussian vector. And given x, this vector here, involving these two quantities, is an affine transformation of vector y. Hence, it is a Gaussian vector with components that are jointly Gaussian. Since we obtained 0 when we computed the cross covariance, then Q tilde Hermitian y and identity minus P times y are conditionally independent given random vector x. If this is eta and this is gamma, then the joint PDF of eta and gamma is the integral of the conditional PDF of eta and gamma given x times the BDF of x. The conditional joint distribution can be written as f of eta given x times f of gamma given x. Eta itself is independent of x. Given x, eta is Cn with a mean that is equal to 0 and a variance that is equal to Q tilde Hermitian Q tilde, which is 1. Unconditionally, eta is Cn 0, 1. This distribution is f of eta, which can be taken outside the integral. The remaining integral is f of gamma, which means that eta and gamma are independent. Therefore, any function of eta and any function of gamma, these two quadratic forms are independent. Ratio rho is equal to the magnitude squared of x Hermitian over the L to norm of x times y, divided by the L to norm squared of y, which is y Hermitian Py plus y Hermitian identity minus P y. The projection matrix P is 1 over the L to norm squared of x Hermitian. Y Hermitian Py is 1 over the L to norm squared of vector x, y Hermitian x Hermitian y. This is the magnitude squared of x Hermitian over the L to norm of x times y. This is exactly what we have in the numerator. Rho is equal to 1/2 a chi-squared random variable with 2 degrees of freedom divided by the same random variable plus a random variable which has the PDF of 1/2 times a chi-squared random variable with 2 times n minus 1 degrees of freedom. So rho is equal to a over a plus p. A is 1/2 chi-squared with 2 degrees of freedom. P is 1/2 chi-squared with 2 n minus 1 degrees of freedom. A and B are independent. Note that when we condition on x, rho has the same distribution. So rho is independent of x. X and y play a symmetric role in the expression of rho, so rho is also independent of y. From the very beginning, we could have written rho as the magnitude squared of y over the L to norm of y Hermitian times x divided by the L to norm squared of x. If we have chosen to condition on y, we get the exact same results. Let's define the random variables c and d. C is equal to a, d is equal to a over a plus b, so b is equal to c over d minus c. The joint distribution of a and b is e to the minus a, b to the power n minus 2, e to the minus b over n minus 2 factorial. The Jacobian of c and d with respect to a and b is 1, 0. We don't care about what we have here. Then minus a over a plus b squared. The absolute determinant is a over a plus b squared, which is d squared over c. The joint PDF of c and d is the joint PDF of random variables a and b, with a replaced by c and b replaced by c over d minus c. So this joint PDF is 1 over the factorial of n minus 2, e to the minus c, c over d minus c, all to the power n minus 2, e to the power c minus c over d. Note that c is positive and d is between 0 and 1. The BDF of ratio rho is exactly the BDF of random variable d. This can be obtained via integrating the joint BDF of random variables c and d with respect to positive c. We have integral c from 0 to infinity, c over rho squared, 1 over n minus 2 factorial. We can take c from here as a common factor, that's c to the power n minus 2. We also have 1 over rho minus 1 to the power n minus 2. We can combine these two exponentials as e to the minus c over rho. This is equal to 1 over the factorial of n minus 2, 1 over rho squared, 1 over rho minus 1 to the power n minus 2, integral c from 0 to infinity, c to the n minus 1, e to the minus c over rho. This integral is rho to the power n times gamma of n, which is n minus 1 factorial. N minus 1 factorial over n minus 2 factorial, that's n minus 1. Rho to the power n multiplied by this part here is 1 minus rho to the power n minus 2. This is the PDF of rho. Rho is a beta distribution with parameters 1 and n minus 1. If u is beta with parameters r and s, then the PDF of u is u to the r minus 1, 1 minus u to the s minus 1 over the beta function of r and s. In our case here, we have 1 over beta of 1 and n minus 1. That's gamma of 1, gamma of n minus 1. Upstairs, we have gamma of the sum, which is gamma of n. Gamma of 1 is 1. Gamma of n over gamma of n minus 1 is n minus 1.